Hello, good morning, everyone. My name is Zander, and today I'm giving a talk entitled Stretching the Truth, Attacking the Elastic Agent. A little bit about myself. I just finished my Bachelor's of Science in Computer Science with a focus on cybersecurity at Oregon State University. And this fall, I'll be beginning the Security Studies program at Georgetown University. Right now, I work as a security analyst in the Security Operations Center here at Oregon State University. And the slides and exploit code for this talk are available on my GitHub. So a quick agenda to cover for this talk. First, I'll be talking about the architecture of the Elastic Stack and the different components that make it up. Then I'll be doing a deep dive on the Elastic Agent, talking about how it's managed, how it's installed on disk, and what features and capabilities it offers. Then I'll cover the vulnerability that I discovered as a part of my research. And then I'll go through a deep dive on how I exploited it and the different primitives that I utilized. I'll give a quick demo of the exploit, and then I'll have some closing remarks about how it was patched and things like that. So first, let's cover kind of what is Elastic, if you're not familiar. It started as a collection of these open source tools for log ingestion and had three main parts: LOGSTASH, Kibana, and Elasticsearch. And since then, over the years, it's grown into this fully fledged large company, international offices, they have enterprise cloud offerings, and they've pivoted into having many different offerings for enterprise search, log analytics, and they've had a strong focus on security in the last couple of years. They built out SIM capabilities in Kibana, and it's definitely showing that they're trying to build out this strong security play, especially with the recent acquisition of an endpoint security company named Endgame. The whole stack is called the Elastic Stack, everything put together. If you've heard of the term ELK, that stands for Elasticsearch, LOGSTASH, and Kibana, but now there are more than just those core three, so they pivoted their branding and switched it to be called the Elastic Stack. And a vast majority of all of the code that they utilize is open source on their GitHub organization. So if you're doing any research or you're curious on anything works, chances are the source code for what you're looking at is publicly available, which was super helpful in my research. So first, there's Elasticsearch. Elasticsearch is the core component that everything talks to and relies on, and acts as a distributed database that scales horizontally, but it provides very powerful search and analysis capabilities. It uses a search language query called Lucene, and has a full HTTP REST API that you can use to interact with it. And Elasticsearch is written in Java. Next, we have LOGSTASH, which is the data ingestion and processing pipeline that's used to take data from various sources. There's a TCP endpoint, there's the Beats protocol, HTTP, Apache Kafka is another popular one. And so it takes all the data in, and it has different ways it can filter and parse and ingest this data and do enrichment on it for things such as GeoIP or different ways you want to enhance your log data to make it more useful. And then it can do normalization, filter on it. If there are different log lines you don't want coming into your Elasticsearch to keep things trim, you can filter them out in LOGSTASH. And then it has many different types of outputs. Elasticsearch is the primary one. You can also chain LOGSTASH instances together. This can be useful if you have multiple pipelines or more of a complex distribution of LOGSTASH instances. And it's written primarily in Ruby. Next, we have Kibana. Kibana is the main visualization and GUI platform for the Elastic Stack. It has dashboards, visualizations, it can do alerting, provides a very good interface for searching in all of your data. It also has a nice SIM feature, which is used for people using it for endpoint security and security analytics, a good way to configure alerting and monitor all the events in your environment. As a web application, it was written in TypeScript. Next, we have the Beats. Beats are these lightweight packages that you install on the endpoints in your environment, and it's used to collect log data and information about a system and ship it into the rest of the Elastic Stack. Traditionally, the Beats are configured to write directly to Elasticsearch, but it is possible to configure them to write to LOGSTASH, but there's some extra work that has to be done to ensure that the proper configurations exist in Elasticsearch. So you have to do some manual work, but then you can have more customization for how you process the data in LOGSTASH. There are different types of beats for different use cases. For instance, a file beat is used to monitor just log files on disk, be it like your web server logs, DNS logs, things like that. Metric beat is used to collect system metrics, things like CPU usage, memory, disk usage, running processes, things like that. Next, we have packet beat. Packet beat is used to monitor the network traffic on a system. If you've used Zeek or Suricata before, it provides some similar function to that. And then there are many other ones, especially like WinLogBeat, which is used for monitoring Windows events. And then the Elastic Agent, which is what the primary focus for this talk is a special type of beat. We'll talk more about Elastic Agent later. And then these are all written in Golang. So the overall architecture for the Elastic Stack has a few key components and then different things you can kind of splice in and add to the system. So on the left, we have our different beats. In this case, we're monitoring Nginx logs, Apache web server logs, and Golang logs. Or it could be Golang metrics for like application monitoring or something like that. Then these are all pointed to LOGSTASH, so additional filtering and enrichment, different ingestion strategies can be utilized on the data. Then it gets indexed into Elasticsearch, and then Kibana talks to Elasticsearch to query the data, aggregate visualizations, build dashboards, things of that nature. So now let's talk about the Elastic Agent. So primarily, when you deploy a beat onto a system, your system administrator will have the binaries from Elastic, and they'll write some config that defines what needs to be collected, how it should be collected, and where does it get output to. But with the Elastic Agent, it's a way of deploying these centrally through Kibana using this new management interface called Fleet, and then configuring them all centrally and pushing out updates instead of manually having to go out to the system and tell it what needs to be collected. It's built on top of the existing Beat framework, and it pulls in all the existing Golang information, but now it uses this different management style that makes it a bit easier for sysadmins to configure how things should be collected on the system. In Fleet, you can configure different policies and information about integrations. So if you have Zeek or Windows event logs or different types of data that you're collecting, you can configure that in Fleet, and then agents will periodically pull Fleet to pull the latest configuration information, so they always know what they should be collecting and how they should be collecting it. And I will mention that Fleet is recommended strongly by Elastic, but it isn't required yet. I wouldn't be surprised if in the next 6 to 12 months, as they move towards Elastic 8.0 and they're pushing out things to general availability, if this does become more of a required feature, but right now it isn't. You can still manually deploy your beats. So this is the main Fleet summary interface, which shows the different pieces that you have available. Top left is the integrations. Integrations are different types of pre-built configurations that are available for your agents. They're usually application specific. So if you have Zscaler logs, Zeek, Nginx, Apache, things of that nature, there are pre-built integrations that you can use, and you just tell it, these are where my logs live, and then it knows how to properly parse the data, how to enrich it, things like that. It can automatically add GeoIP information, things of that nature. And then you can configure those integrations to be tied to policies, which is what the top right shows. There are different policies you can configure for your agents. An agent can only be enrolled in one policy at a time. The agents shows all the different agents that you have in your environment, and then you can view them, you can unenroll, you can enroll new ones, things like that. Then at the bottom right, we have data streams, which is a new way of collecting data in Elasticsearch, and I have a few slides on data streams that we'll cover later. So now let's talk about the enrollment process of how do you get a new agent actually deployed in your environment. So first, you have to initialize Fleet, and this has a new Elasticsearch user associated with it called Fleet_enroll, and that user has permissions to generate new API keys in both Elasticsearch and Kibana, and that gets utilized when you deploy a new agent. It generates unique credentials for that agent, so there are no shared credentials being used across the environment for any sort of persistent way. Then you have an enrollment key, which is generated in Kibana and is tied to a single policy. That's used for this initial authentication into Kibana to begin the enrollment process. Each policy has one enrollment key, and it's a one-to-one relationship. So that's how the agent is identifying which policy it's supposed to be enrolled in. So when we first deploy Fleet in Kibana, we're greeted with this menu. So we just have to click that big Create User button, and that will initialize the proper user, set up the permissions, and begin creating API keys as we enroll our agents in the Fleet. So once we do that, we can first create an agent policy on that Policies tab. So we'll click that big blue Create Agent Policy button, and then we'll be greeted with this basic config. So we can give it a name, give it a description, and tell it what types of data we want to be collecting and the namespace that should be collecting it. Next, we will configure an integration. So for this, I've made a new policy called Windows. I'm going to go ahead and click that big blue Add Integration button, and then we'll go ahead and search for Windows in that dropdown. And then we can configure different types of specific settings for our Windows integration. For the different types of data you can collect, it collects from system events, security events. It can also collect PowerShell logs and sysmon data if you're configured for that in your environment. It can also collect perfmon and service metrics. As I was developing my exploit and debugging things, having all that metric data come in very quickly definitely made things a bit more difficult. So depending on your environment, what your use case is, it may be nice to have that, but be aware that it does take up a fair amount of space, especially in a large environment. So now that we have our policy, we've configured an integration, we can now enroll an agent that will receive the integration. So we'll click that big blue Add Agent button, and then we can select the policy associated with the agent, and then we're greeted with this command line that we can use for Linux and macOS, or a separate one for Windows for the proper syntax. And so the two key components in this command is the Kibana URL, which explicitly states the protocol, full host name, and the port. The default port for Kibana is 5601, but it can be configured to run a different port, or you can put a load balancer in front of it, whatever works best for your use case. And then there's the enrollment token. And like I mentioned, the enrollment token is a one-to-one mapped to a policy. So as the new agent authenticates into Kibana using this enrollment key, that's how Kibana knows which policy needs to be tied to this agent and gives it the proper configuration information as a part of the initial enrollment process because of that key. So now let's go ahead and step through the actual provisioning process. So first, when we first run that command that I showed on the previous slide, the agent will make a post request to Kibana to this Fleet's agent enroll API endpoint, and this authenticates with that Fleet enrollment key. So now Kibana knows what the policies should be, how it should configure things, and so it generates an appropriate access API key that's going to be used excuse me, for future authentication requests into Kibana. Next, the agent will make another post request to this check-in endpoint. And this is authenticating with that access API key. So now that's being used for future authentication requests, and that key is stored on disk and it's persistently used by the agent. Then Kibana generates a new policy. It configures the agent for what it should be collecting, how it should be collecting it. And as a part of that policy, it configures the Elasticsearch output so it knows where to be sending that data. And that is an authenticated request to Elasticsearch. And so it contains the API key that is being used to authenticate all of those requests into Elasticsearch. Next, now that the agent has its full policy from the fleet management system, it can begin talking to Elasticsearch and ensure that the authentication works correctly. So first, it just gets the index route to validate that the API key is working properly. And this returns a 200 OK. Next, the Elastic agent checks in with Elasticsearch and gets the license information for the system. Again, this authenticates with the API key, and then this returns a 200 OK. Finally, it has finished its initial configuration process and it can begin uploading data into Elasticsearch. This is done by making a post request to the _bulk API endpoint, again, authenticating with that API key for Elasticsearch. The _bulk endpoint is used to upload multiple documents at once, which makes it much more efficient to be sending data into Elasticsearch. So there are a few different credentials that we've talked about that are being used in this environment. So first, there's that fleet enrollment key, which is exposed to the system administrator in Kibana as they do their initial agent enrollment. That's only used once. And then as a part of that, the Kibana access API key is generated and stored on disk for the agent to use for all future Kibana requests. Finally, there's the Elasticsearch API key, which is also stored on disk and used for all connections to Elasticsearch that require authentication. And these are both generated by that fleet enroll user, and they're unique per agent install. So the same API keys shouldn't be found on more than one endpoint in an environment. Now let's talk a bit about the actual structure of the agent and how it operates. There are two main beats that it relies on to do its actual data collection, file beat and metric beat. And depending on how you configure your agent, it's possible that other beats could be deployed as a part of that policy, but these are the primary two you're going to witness in your environment. It's configured to ship logs directly into Elasticsearch, but it is possible to reconfigure things to ship them into LOGSTASH. And it checks into Fleet via Kibana on a regular interval that's defined in this configuration. The agent has two different processes that it runs so that it can ensure data redundancy and make sure that if one of the processes crashes for whatever reason, another one is ready to go monitoring that data. So there's minimal downtime and loss of visibility on a system. Here we have two file beat processes running, and then if you have metric beat configured, it would show up there as well. The Elastic agent, as a part of its installation process, it registers a Windows service. This provides a couple benefits on the system. Firstly, if the agent crashes for whatever reason and the full service fails, that will generate a log on your system, so you can go back and check, oh, wow, what happened to my visibility? Did something happen? You may be able to find something in your system event log, and there are similar logging utilities on Linux as well. Secondly, if the system is rebooted for whatever reason, this is configured to start up automatically at boot. So when you turn on your system, the Elastic agent will pick up immediately and begin shipping data back to Elasticsearch. This is the primary directory that Elastic agent is installed into. It's at C, program files, Elastic agent. There are a couple key files in here. One is this fleet.yaml file. Then there's that data directory. It also has a symlink to the binary, which lives a few trees down in that data directory, but it's available right there for more convenient access. So in that fleet.yaml file, we have that Kibana access API key, along with the URLs for the Kibana endpoint. It talks about how we should do SSL and how it should be communicating to Fleet, things like that. Next, we have this data directory, which is there's the agent, then this data directory, and then the Elastic agent. And here we have this 1DA173. That is a partial hash value that is unique per agent version. But if you have the same version of the agent installed in your environment, it should be the same hash. I believe it's a artifact of the build hash, I think, or something like that. But it's the same across those versions, so you can rely on it for the singular version you have deployed. Here we have this key file, this action_stored.yaml, along with the actual binary that symlink is pointing to. So in the action_stored.yaml file, this is where the full policy details are stored. And you'll see that this is nearly a 10,000 line file. All those data streams that I have collapsed, that actually tells it what Windows event logs to collect and how it should parse it and normalize it and then send it off into Elasticsearch. Then as a part of this policy configuration, it does know where Fleet is, although it doesn't have the authentication information directly in this file. And it also has the outputs. And here we're outputting to Elasticsearch, and we have the API key stored in the action_stored.yaml file. So I mentioned data streams a little bit earlier. Data streams are used as a newer way to store data that's being collected for a long period of time, but you still want to be chunking it up into smaller, more manageable indexes. Traditionally, you would be manually creating these indexes, and then when you start using beats, the different beats will create their own index in Elasticsearch when you have the Elasticsearch output configured. When you're outputting to LOGSTASH, it's up to you to configure your LOGSTASH output to make your Elasticsearch indexes accordingly. But now with data streams, instead of having to manually organize the indexes you want to utilize, it provides this nice append-only manner of organizing your indexes where you only have to write to a data stream. Then Elasticsearch internally figures out how to chunk it up into indexes so it can achieve the proper replication and redundancy for your data. So when you want to read from a data stream, all you have to do is make your search request to that data stream instead of to an index. And then internally, it figures out where in the data stream that data lives. And then it returns it to you just like you were querying an index. Next, when you want to write into a data stream, also known as indexing, you'll make your index request into the data stream, and then Elasticsearch will again internally figure out which index the data needs to get written to, and it will identify if a new index needs to be created. And then it will write the data just like you're writing to an index. So now at this point, let's quickly recap kind of what we've covered and what we know. So we know that we have this Elastic agent. It checks in with Kibana periodically using that fleet management interface. We know that all the data being collected by the agent is being written into Elasticsearch. We also have the API keys for both of these, and we've identified where they live on disk and where an attacker could possibly recover these API keys. So at this point, I wanted to identify what are the privileges associated with these API keys, and what can an attacker do if they uncover these API keys and want to do something malicious against the Elastic Stack. So I found this very helpful endpoint in the Elasticsearch API, this nice has privileges API. And so what the has privileges API allows you to do is you can check the given permissions associated with the user on a specific index. And it's very handy. You have to be a super user to check any user, but anyone that has authentication into Elasticsearch can check what their own permissions are. So this is fantastic. I can have an easy way to enumerate the permissions using a pre-built API endpoint. So there were two key pieces of information that I needed to utilize this endpoint. First, I need to know an index to check the permissions of, and then I need to know which permissions to check. So the target index was the first thing I set out to identify. In Kibana, since we are coming at this from a security researcher perspective, I can take some shortcuts that make it a little easier for me to figure out what's happening. So I can go into Kibana, check the data streams, and then if I click on a data stream, it will tell me all of the indexes that exist in the data stream. So it's very easy for me to identify an index that I knew would exist that I could check the permissions of. However, it is definitely not necessary for an attacker to have access to the administrative section of Kibana. The names of the data stream indexes are deterministic, so they can just generate a list of the ones that should exist. They can check them against the environment. So the different components is the name of the data stream. These are default names that an attacker can identify on their own. The date it's created in the generation, which serves as like a counter value to ensure that there are unique indexes in case multiple are created on a single day. Next, I need to identify a list of permissions to check. I found a helpful Elasticsearch documentation page that has all of the possible permissions for an index. So I just grabbed all of those and threw them in a list to provide in my API request. So the couple key ones that I noticed are these delete and delete index ones. I knew that if an attacker can delete data from these indexes, that would definitely be a big problem. So those were two that I was particularly interested in seeing if those were available. So I wrote a quick script that given a Kibana URL, API key, and the name of an index to check, it can log in and make that API request to see kind of what's going to happen. And so I was checking for this data stream index for Windows PowerShell logs, which is one of the data streams utilized by the Windows integration for Elastic Agent. I saw that it does indeed have that delete permission. So I knew that there was some vulnerability here. I was allowed to delete data from Elasticsearch using this API key that could be recovered by an attacker if they compromise an endpoint in an environment. So this was fantastic. So now I just needed to work on building a proper exploit for it to demonstrate impact before I sent it off to the Elastic security team. So I began reading the Elasticsearch documentation to try to delete some data from my lab environment. And then I realized that I was going to need a document ID to identify which documents I wanted to delete from Elasticsearch. Unfortunately, there was not an easy way to recover this, and the document IDs are much too high entropy for me to brute force reasonably. So I was trying to figure out a way that I could possibly query the data, so I can ask Elasticsearch for some document IDs that I'm interested in, it can return them to me, and then I can delete them. So there was this very handy delete by query API endpoint, but unfortunately, the RBAC in place does require re-permissions for this API endpoint, and there were no re-permissions available. And I checked and I tried a couple different ways to see if I could maybe get something like this to work, but unfortunately, I wasn't able to find a bypass or a way I could query the data and delete off of that query. So at this point, I kind of went back to the drawing board. And I have some advice I'd like to impart on all of you. If you ever find yourself in a situation where you're just banging your head against the wall, trying to find a solution to some arcane technical problem. Taking a break is key. Go bowling, listen to some music, just take a break and let your mind rest and subconsciously process the problem you're trying to solve. Going outside is a big one. Get away from the computer, take a break, enjoy some nice Oregon rain. And remember that computers are bad. They're evil, and they make our lives difficult sometimes. This is kind of what I felt like doing to my computer as I was working through this process. But eventually, as I followed the sage advice after ignoring it for far too long, I came up with an idea that I thought might work in this situation. So I knew that one place where the document ID was going to be available is in the actual HTTP traffic. When you use the Elasticsearch API to upload these documents, the response contains the ID for the document that was created. So I knew that there was going to be available in the HTTP data, but I wasn't sure how I was going to get it. The only way that we can sniff and view this traffic is in the file-B process. All this communication is happening over SSL and TLS, so I can't sniff it from the system itself. I have to somehow become a part of that client to view that traffic and analyze it. And so I started thinking of a way that I could do this. And so I knew that my goal, I need to intercept the requests and the responses, find some documents to delete, grab out their IDs, and then delete them from Elasticsearch. And so my plan for this was that I was going to somehow inject some code into Filebeat that could accomplish this goal. And so I wasn't sure how I was going to do this, but I knew I could use my trusty IDA to pull up the code and find a way that I can inject something into it. So first, let's talk a little bit about the structure of these binaries. Like I mentioned, all these beats are written in Golang, including the main Elastic agent system. If you haven't had the opportunity to work with the Golang ABI, the application binary interface, it's definitely a fun non-standard system that you're not familiar with before. Golang has some really powerful capabilities. It makes it really easy to write Golang source code, but analyzing the binaries is definitely less trivial. It's also a static binary, which made it quite large. It was 80 megabytes and had all sorts of third-party library code integrated into it. So there are minimal dependencies required to be shipped with it. It also had all of its symbols stripped, so I wasn't able to identify functions very easily in IDA, and it only automatically detected 1900 functions. And I had a feeling that was going to come in way under the actual amount since it was such a large binary. 1900 functions just seemed way too small. So my first quest was to get some symbols into a binary. Since it's open source, this was a big game changer for me in my analysis process, because I knew that I could somehow figure out how they were stripping the symbols and get them back in, which would definitely aid my analysis. So I used my trusty grep, and I was able to find this in the part of their build script. They used a build system called Mage, which is a Golang build environment. And they're passing this flag to the linker with -s, which will strip all of the binaries from all of the symbols from the binary. So I commented out this line, and I was able to compile a binary that had symbols, which was awesome. It was a much larger binary. It's about 100 megs larger at 180 megabytes. I mean, it took IDA nearly an hour to analyze, and the output IDA database was over a gigabyte. So it took a long time to analyze, but it found way more functions since it had all that symbol information. It had over 100,000 functions identified, and it made my analysis much easier. One nice thing about IDA is that even when you have these massive binaries with these large databases, the bulk of the time you're wasting by watching the analysis go is at the very beginning when you first open it. Once you have this database saved, it's quite efficient to actually search the database and do your analysis. Ghidra is another alternate tool that I could have used for this, but I'm a bit more comfortable with IDA, so I stuck with that. But Ghidra, I'm sure, has other ways that it handles these very large files. So now I knew that I needed to rely on the power of open source to solve my problems. These large binaries with over 100,000 functions, it wasn't going to be feasible for me to analyze these in IDA to find some sort of way I could manipulate the code. So I pulled the open source, I downloaded it, and I started grepping for various keywords, such as post, underscore bulk, which is that API endpoint that I was looking for, and just generic HTTP code in case there was some common library it was using to make all these HTTP requests. And so I knew that I needed some way to validate the results as I was looking for functions and thinking that these may work. There's complex logic flow happening in this binary. I'm definitely not a Golang expert, and I was having difficulty actually tracing the flow by reading the source code between what functions were being called. VS Code's analysis of which functions were being called wasn't super accurate. So I knew I needed something that was a bit more dynamic to allow me to really identify, is this function going to have the information I need to pull out the request and the response? So I used a Windows debugger called x64debug to set breakpoints on various functions and instructions that I was interested in to analyze the data on the stack and the heap and the call frame to see if this was going to be a good candidate and warranted further investigation. So this is the general flow that I used as I was looking for a target place to add my malicious code. So first, I would find something interesting in the source code, usually from my grepping, but I also did some manual analysis through directories that looked interesting and seemed relevant to the HTTP code. Then I would find that function in IDA with the debug binary, and then I would pull some information from the debug binary to look for that same function in the stripped binary. And then I would take the address of the function in the stripped binary, set a breakpoint on it, and then analyze what's happening in memory to see if it's going to have all the data that I need. And then I just repeat this process and try to find something that will work. So first, let's look at the source code. So here I've done a grep for HTTP, and I found this function called exec HTTP request, which is operating on this connection interface. Next, I pulled up this function in the debug binary, Because it has the full symbols, it has these very verbose function names that make it very easy to find the function that I'm looking for. So I was able to quickly find this exec HTTP request function, which is operating on that connection interface. And then I pull it up and I'm able to look at the function, see what it looks like. And then I switch to the hex view. In the hex view, I pulled a few bytes of the function and copied them, which I dubbed as canary bytes. And I was using these to search for that same function in other binaries, in this case, in that non-symbol binary. I did this so that I could have a reasonable way of finding it because it's not identifying the functions. I knew that because there was different information present in the binary, the address wasn't going to be the same. So I went to the search binary and I pulled up the binary search menu in IDA. Then I searched for those bytes and I was able to find that same function. As I went through my searching, this strategy wasn't always successful. Some functions had different data at the beginning, so I had to use different strategies and pull out some bytes in the middle and do some guess and check work to see, does this line up with what I'm expecting it to, and is it similar enough to the debug binary that I feel confident that's the same thing. So now that I found the binary in the non-debug binary, I found the function, I will go to my debugger, I will attach to the file B process. Then I will use the go to expression menu to find that function, and I'll put in the address that I identified in the non-debug binary, and then I will set a breakpoint on it. So at this point, I've set a breakpoint in my debugger and I'm ready to do my analysis. So all I had to do was just generate an event that should cause something to be sent to Elasticsearch and see if it hits my breakpoint. And then as I hit the breakpoint, I could check the stack and the heap and the call frame and see if it's picking up the information that I need. And so eventually I found some success, which was very awesome. The magic place that I found was right after this ioutil.readAll function that's being called on line 469. What's happening here is that it's reading the actual bytes from the HTTP response into memory within this function. So I was able to find offsets that have the response body at RSP plus aux18, the request body at aux58, and then I found a bonus piece of information, which was the actual authorization header that had the API key. So it could have been possible for me to not even have to grab the Elasticsearch API key from the config. I could have just taken it right out of memory and utilized it. So I had all three of my pieces of information, and now I set out to build an exploit that could utilize this information to delete some information from Elasticsearch. So at this point, I kind of had an idea of what the problem, how the problem could be solved, but I didn't know exactly how to accomplish it. So my general strategy was to utilize a technique called DLL injection to inject some malicious code into the filebeat process, and then do some in-memory patching of the existing filebeat code to ensure that execution will be handed to my malicious code after we've executed the ioutil.readAll. So I have my data available, I can make my malicious code, and then I transfer execution back to the existing filebeat code so that it looks like nothing has ever happened. So now let's talk about DLL injection. It's a very simple technique that can be utilized to take a malicious library and inject it into a different process's memory space. It uses primarily three different APIs in the Win32 set. And it's one of the more simpler techniques that can be utilized to inject code into a process. And it's something that's been commonly observed used by malware. So the first API call that we have to make is this virtual allocx function. And this is very similar to malloc, and it allows us to allocate memory in the target process. And that's what we're going to load our malicious code into. So in this case, I allocated enough memory to contain my entire malicious DLL file. Next, we will make a call to write process memory, which allows us to actually take the bytes for our DLL and write it into the target process's memory space. And we'll be writing this into the memory space that we just allocated using virtual allocx. Finally, we'll use create remote thread, which we can utilize to call a function in a new thread in the target binary process. So for us, we're going to be calling load library A, which will initialize their DLL that we've injected into the process. And the way this works is we just pass in the name of the library, and it knows that it's been loaded into memory. And then we can call load library A, which triggers the initialization function of our DLL. Within that initialization function, I can set up the malicious code that I'm overwriting the filebeat process, and set up everything so that I can seamlessly inject into the code. So now that I have code execution, I needed to figure out what I was going to do to the actual file beat code to transfer execution to myself. So there were a few different questions that I asked myself that I knew I needed to solve. First, are there any protections that could break this? Things like DEP or ASLR, any control flow hardening, things that would eliminate my ability to just simply inject malicious code into the process. Secondly, I need to identify exactly where my code would go. Third, I need to identify what I was going to put there. So first, let's talk about memory protections. So the only one that impacted this is called DEP, which stands for Data Execution Prevention. On Linux, this is called no execute or NX, but these two technologies are effectively the exact same thing. And what it boils down to is that memory can't be writable and executable. So places like the stack and the heap, if DEP or NX is enabled, those sections of memory are readable and writable, but they are not executable. And this is to prevent an attacker from easily exploiting a buffer overflow vulnerability and just loading shellcode directly into memory. However, due to the way that we're available in the system, we can actually just change the permissions of memory. So in the screenshotted code, I'm calling a function that I wrote that enables read, write, and execute permissions on the text section of the filebeat binary, which is where all of the code lives. So previously, it was just readable and executable, but then I add the right permissions so I can install my malicious patch. And the DEP technology has been available in Windows since XP and Server 2003, so it's very common nowadays. So that solved my first problem about memory protections. Secondly, I needed to identify the exact address of where I was going to begin overwriting code. So I knew that I could go right after that ioutil.readAll function returns. So I chose the address A8CCB1 as the place to add my malicious code. Thirdly, I needed to figure out what I was going to do. So let me kind of walk through the execution flow as I talk about the different parts of this exploit. So first, we have the legitimate filebeat process. All of its code is normal, it's executing the things that was put into it by the developers, and everything is all good. Next, I inject a small piece of malicious code called a trampoline. And what the trampoline does is it overwrites some of the legitimate code already right after the ioutil.readAll returns, which transfers execution to my malicious code. So this is the actual bytes of code for my trampoline. For me, I only needed to put the address for the code I was going to be jumping to, and then actually execute my jump instruction. In this case, I wasn't able to actually fit my entire exploit onto the memory because I didn't want to complicate things between different function calls that overwrite too much. So I chose to redirect execution to a different part of memory where my actual malicious DLL lived, and only overwrite a very minimal amount. So now that we've had our trampoline code execute, it transfers execution to my full patch. So first thing in the patch is I set up this call to some higher level C++ code. And to do that, I need to meet the calling convention being used by the Windows compiler. So the way the calling convention works is the first argument goes in the RCX register, the second argument goes in the RDX register, and the third argument goes in the R8 register. So I grabbed the data from the stack the way that I had identified using my debugger. So the request data was at aux58, and I'm setting that up on line 69 and 70. I had to dereference a pointer twice for that. On line 68, I'm pulling the response data, which is at aux plus 18, and then I pulled that API key at aux plus 88. Finally, I make a call to my C code, which I loaded in at a fixed address. I set up a small function table that had the static addresses for my code, so I knew it was always going to be available at a place I could access it. And then if that address, that 66420100 address is not available, the exploit just aborts, so there's no chance of crashing the process. So now that we've done this, we've transferred off to our C++ code, and the rest of the patch handles the code that just got replaced by the trampoline. So it executes that code. And this is the way that I added the exact instructions into my assembly code. I just put the raw bytes that represented the opcodes. So when it's actually compiled, it will execute those as instructions. And then I jump right back to the code that I at the end of the trampoline. So the filebeat process continues executing exactly as normal. So now we've done our patch, we're handing off execution to our C++ code. And this is where like the full meat of the exploit lives. So in the C++ code, unfortunately, it was too long for me to adequately put on the slides, but the way it works is I search that request body for target keywords. In this case, I used a keyword maluser1 as just a small way to demonstrate the impact of the vulnerability. So a common use case this could be is if an attacker is brute forcing some user, they could put that username as a target keyword, brute force that user, and none of those failed authentication logs would make it into Elasticsearch. If it's found, it parses out the document ID as a part of it, and then it uses the built-in HTTP API code in Win32 to make that request to Elasticsearch to delete the document. The slides are available on GitHub, and you can click that hyperlink to view the full HTTP function. So now we've executed our C++ code, we've deleted any documents that need to be deleted. Now we need to make sure we get our code back to the fileb.exe legitimate code. So the patch will execute that replace code that I mentioned, and then the replace code transfers execution back to the trampoline right where it ends. So from the fileb process, it's executed all its normal code. The function that we replaced part of has executed normally, everything continues. But we've actually injected our malicious code that deletes some data from Elasticsearch and allows us to manipulate the data. So now I'm going to transition into a quick demo to showcase this exploit. So first, I'm going to generate a log that will be a failed login for this ASDF user. Then if we refresh Kibana a couple times, we will see that we have this failed login for the ASDF user. So we know that the agent is working properly, it's collecting the event logs, and it's shipping them into Elasticsearch. So now I'm going to run my exploit, which will inject my malicious code into the binary. It writes that trampoline, fixes memory protections, all that stuff we just covered. It looks like it was stable, and it has successfully injected it. This is an example of the log for that exploit. There are a few different things that it shows. First, it shows on that third line that the permissions were not executable, readable, and writable, so it set some new permissions. Then it installed the interception patch, which is the HTTP C++ code that I mentioned. It installs the patch, it installs the trampoline, and then it finishes all of its initialization. So next, I'll generate another login event that won't be filtered to show that the Elastic agent is still working properly and fileb is shipping data into Kibana. Perfect. So now we see that ASDF2 user, it has a failed login just 13 seconds ago, and so we know that the agent is still working properly. So next, I'd create this failed login using this maluser1, which is being filtered out by the exploit. So we see it hasn't showed up in Kibana. Then we can check the log being utilized by the exploit. So here we see that we did execute the HTTP code. We were able to transfer execution to our injected code. We intercepted a request with that malicious user, and then we parsed out the document ID and were able to successfully delete it from Elasticsearch. So the exploit worked perfectly and there were no issues. And we can double check Kibana and we see that it has not shown up in Kibana. So this vulnerability was patched as a part of Elastic 7.12, which was released on March 23rd earlier this year. And the way this was patched was they changed the permissions associated with the API keys that were being issued by Fleet and Roll. As a part of some future work to remediate this and to prevent things like this from happening in the future, they're creating new roles in Elasticsearch that have better append-only structures so that there's no accidental delete permissions associated with users. And you can click on these hyperlinks to view the Kibana issue, the Kibana pull request to patch this, and an associated Elasticsearch issue for some of that new stuff. Finally, I'd like to mention some future research that can be done here. The Elastic agent, it's still in beta. It's not being recommended for full production use, but it's moving close towards a general availability release. I expect probably soon, or maybe as a part of the Elastic 8.0 release, that we're going to see this hit general availability. As a part of this, they're actively adding more features and building out their capabilities. So a great place you can keep an eye out for things is on the GitHub issues. Since this is an open source project, it gives us a lot more capability to see what's happening and what possible vulnerabilities may live in the system. So you can keep an eye on those issues to see if anything catches your eye that may be a security vulnerability or something that indicates a possible security problem. There's also this full fleet API that I haven't had a chance to do a ton of in-depth work on. It's possible there are some like access control or different vulnerabilities that exist there that could provide some additional Elastic agent issues. Another possibility, since we are working with these compiled binaries, is the possibility for some sort of binary vulnerability, like a buffer overflow, format string, things of those nature. It's very unlikely, since it is written in Golang, there are a lot of memory protections built in as a part of the Golang compilation process, but it's possible. Anything's possible. So there's a chance that there are some there that exist. Then, of course, there's the actual EDR capabilities. Since Elastic purchased Endgame, they're building out a full endpoint detection and response feature that's available as an integration into the Elastic agent. I haven't had a chance to do much work on that, but there's a large attack and bypass surface available in that EDR software. I think there's a lot of work that can be done there to find some new vulnerabilities. So thank you very much for coming to this talk. I hope you enjoyed it. I look forward to answering your questions, and the slides and exploit code mentioned in this talk are available on my GitHub. Thank you.